Now that we finished up talking about capacitors, we're going to talk about some basic circuits and in where current will be flowing. So first we need to define what we mean by current. Current is defined as, so these three lines, we know an equal sign, something is equal to something else. Having the three lines means it's not only equal to, but also a definition. So current, the definition of current is the rate at which charge flows. So current is dq dt. Q still means charge, so number of coulombs. dq dt technically is the derivative of the charge with respect to time. If we have a constant rate of charge flow, if flow is constant, we can say that current would be the delta Q over delta T. Meaning, if we had a wire and we could watch charges pass by a specific point in the wire, there would be a certain number of coulombs per second. So, coulombs per second. This is the fundamental unit of current, but we also call this an ampere, or amp for short. And we use a capital A to represent the units of amps. Now, our current textbook talks more about microscopically what's going on. When we talk about coulombs per second, we're not talking about a total number of electrons flowing and moving all the way through a circuit. So for example, to get current to flow, we have to have a potential difference. The potential difference typically in a circuit, I'm gonna draw a light bulb. So I'm talking a filament light bulb, not an LED light bulb. If I have a light bulb and I connect it by wires to one end of a battery and not the other, then current cannot flow. In order to have current be able to flow in a circuit, there must be a complete path for charges to move through, but there must also be some sort of potential difference supplied to the circuit. So here we're representing a battery. We will still use EMF to represent the ideal battery. As soon as we connect a battery, if you remember, potential difference and electric field goes hand in hand. And electric field lines, or electric fields, point from high potential to low potential. So as soon as we connect the battery and make a complete circuit from one end of the battery to the other, there will be an electric field within the wires. And fundamentally, it's this electric field that exerts the force on the valence electrons and causes them to move. Now, the definition of the direction of current flow was made back in Benjamin Franklin's time. They didn't know the difference at that point in time between a positive charge and let me rephrase that. They knew there was some sort of difference in charge, positive versus negative, but they did not have a way to know which ones, positive or negative, were actually flowing and moving in the circuit. And in all reality, even if we were to set up a little circuit and set up a little light bulb, we also would not know which direction the current was flowing. So we still use the definition of current flow that was made in Benjamin Franklin's time as the flow of positive charges. So we draw current as if it were positive charges moving throughout the circuit. And we use a capital I to represent that current flow, however many amps that happens to be. Realistically, microscopically, it's electrons, the negative charges that are flowing the opposite direction. But mathematically and functionally, it doesn't matter whether we talk about electrons flowing from low potential to high or positive charges as if they flowed from high to low. So we will use this typical definition of current. Our author talks about the actual electrons and what distinguishes, say, like aluminum from copper versus any other metal. We know it's the electrons that move. The speed at which the electrons move is called the drift velocity. Oops, that's not how you spell drift. Drift velocity or speed. And this is on the order of about 10 to the negative 4 meters per second. So the electrons that are moving are not making it all the way around the circuit. What happens is as soon as the electric field is set up, there's charges everywhere throughout the circuit, on every side of the circuit, that start to have a net flow, a net movement. I'm just drawing a few little dots, which you may or may not be able to see very well. These charges are all influenced by the electric field, and motion starts everywhere. I'm not going to talk about this section on drift velocity, and you will not have homework questions or exam questions related to that either. It is an interesting topic to understand what's happening at that microscopic level, but we will not be covering that right now, or at all, actually. So as soon as we connect some sort of source of potential difference, conductively connect it from one end of the battery to the other, we get current flow. The rest of this chapter talks about some general rules we have with current flow. And then it also introduces another element, circuit element, called a resistor. The light bulb I drew right here, the filament in here, this is representing a regular tungsten filament light bulb. So not LED, just a good old-fashioned light bulb. We say this light bulb has resistance. Its resistance, we use a capital R to represent the resistance, and we call this light bulb essentially a resistor. We know if a battery is connected, as that current flows, the light bulb would light up. The light that we see, it also would get hotter, so we would get a light, actual visible light emitted, and the light bulb itself would get hotter. What we see with resistors is they convert electrical energy, so these charges that are moving in this electric field have electrical energy. As the current flows through the light bulb, current is not used up. but energy, some of the electrical energy is converted to, in this case, light and these higher temperatures. It's going to say heat, but our physics definition of heat is not what I mean here. There's an actual resistance to the flow of charges through the wire. So it's more analogous to friction. So it's a thermal energy, if you remember that from Physics 1, which is different than heat. Okay, so the current that I drew on this left side is still the same amount of current on the right side. This is related to conservation of charge. We talked a little bit about that with our capacitors. If we had capacitors in series versus parallel, whatever charge, for example, if we had our battery, we had a capacitor, one here, and then another one over here, and we talk about the charge that accumulated on the first one, but as we think about charges during the time they were moving to reach an equilibrium, so a Q2 and a Q3, as soon as there was a junction here, there was a splitting off of the charge. So the charges that were moving, some of them ended up going to this middle capacitor and some went to the final far right capacitor. Conservation of charge means whatever charges are moving, they just have to keep moving. There's no room to collect charges for any charges to stop anywhere. That is the case with our resistance circuits as well. The current that is flowing in any one single wire has to still be flowing. And that's why we end up with the same amount of current everywhere in this circuit. We will be talking about something that is called a resistor, such that they are connected in series. Now we draw these resistors in a circuit kind of like the filament up here in the light bulb. We just draw a little squiggly line. We use a capital R to represent it, and we will be connecting them to a battery. So in series, the definition of series is the same in that if I follow a path from one end of the battery to the other, the same amount of current in this case. With resistors, we care about current flow, not just a charge, but the rate at which that charge is flowing. And so this current flow will be the same everywhere in this path because there's no junctions for the current to break off and split up into different paths. So resistors in series will have the same current, similar to how we said capacitors in series had the same charge. In parallel, the idea is similar to what we talked about with capacitors in parallel. If we follow a path, here there's a junction. So this time I'm choosing to go through R2. I need to actually fix this. It's not quite valid what I wrote. So let me draw this again. So resistors in parallel mean if we follow a path around a circuit, then there's a choice. So parallel, we always have to have some sort of junction in here, where if we're following the path from one end of the battery, when we get to the junction, we can either choose to take our path through R2, which will get us back to the other side, or we could choose to go up through R1 and back down, which will get us to the other side. What was wrong about what I drew is I can totally draw current coming this way. I'm going to call this the battery current because it's the current that flows in or out of the battery. It comes out of the positive terminal of the battery and goes back in on the negative terminal. But as soon as there's a junction, all of this battery current is going to flow. It's just not all going to take the same path. Some of the current will come up through R1 and back to the junction on the other side. We could call that an I1. But some of the current will go through R2, and we'll call that an I2. Now, in terms of conservation of charge, what we can say here is the battery current continues flowing, but it splits into current that goes to resistor 1 and current that goes to resistor 2. And so we get this relationship that represents conservation of the charge flow. We call this a junction rule. We're going to be talking more about the junction rule, as well as we were talking about loops and looking at voltages as we go around a loop, as we talked about capacitors. We'll be talking about these rules as well as we talk about resistors. But first, let's talk about what we mean by resistance. So resistors are materials that are not really great conductors. Capital R we are using to represent the resistance of a resistor. The microscopic equations and conversation our author goes through derives this equation. I'm going to go ahead and just give it to us. The resistance of a resistor so capital R. This row means resistivity. It is something unique to the material itself. Copper has a different resistivity than aluminum, different resistivity than whatever other material we want to talk about. But it is unique to the material. It's related to what we call the charge density, which is a number of charge carriers per volume, and how often these electrons could potentially run into the nuclei, different atoms within the conductor. L here is the length of the material making up our resistor. And A is the cross-sectional area of the material making up the resistor. So similar to a capacitor, I'm just going to rewrite our capacitor to the side. We've already talked about the capacitor, but just as a reminder, capacitance of a capacitor depends upon the dielectric constant, our constant epsilon naught. It depended upon the cross-sectional area of the plates and the distance between the plates. So the actual capacitance was determined by how the capacitor was made. That's similar for a resistor. resistance is determined by how the resistor is made. What is the material? How long is it? What is its cross-sectional area? Now, the units of resistivity are ohms. This capital omega is an ohm, is what we call it. So it's a Greek letter, capital omega. Length is in meters. Cross-sectional area will be meters squared. So when we plug these units together, we are left with this ohm. These are the units of resistance. This is the value that they've chosen to assign to the resistor. Now, as another reminder, if we go back to the capacitor, capacitors, charge can accumulate on the plates of a capacitor. The potential difference across the capacitor ended up depending upon how much charge was on the plates and then also the capacitance of the capacitor. Now again, I put a subscript of C on there to specifically designate that we mean the capacitor. If we come to our resistor, we find that the resistor, the potential difference across the resistor itself depends upon how much current is flowing through it and the resistance of that resistor. Now, our author writes this initially this way. And the reason why is because the current is a result in having a potential difference applied to a circuit. So kind of like Newton's second law, the net force was equal to mass times acceleration. We originally write it as acceleration is net force over mass. The acceleration was a result or consequence of having a net force. And then its value depended also on the mass. So kind of an analogy here is this current, this flow of charges is a result of having a potential difference supplied to a circuit. How much current flows depends upon the potential applied to the circuit as well as the overall resistance of the circuit. And that's what this is representing. Current is a result of having a potential difference supplied to a circuit. We often write it this way, but of course it's the same equation, right? If I just bring resistor over, I have delta V is equal to IR. Some of you may already be familiar with this. This is called Ohm's Law. It does not apply to any and every type of object, but it does apply to resistors that are ohmic, which of course is a little redundant when you don't know what that means. Ohmic resistors means that if you were to plot a potential difference versus current, we would get a straight line. So many materials are ohmic materials. There are plenty of materials that are not. For those, we cannot use V equals IR. But that's okay. Our resistors that we are going to talk about are going to be ohmic. And so the voltage drop across a resistor will equal the current flowing through it times the resistor value, the amount of resistance. Now, with these units, we could solve for R. R would be delta V over I. We already know potential difference is in volts. We've now talked about how current is in amps. A volt over an amp is defined as this ohm. And so these are the units we will see for our resistors. But that also means if we have an ohm times an amp, we get a volt. So we have some units that we can work with together. Now, our author does not talk about the purpose of a resistor quite yet. Our author waits till the next chapter. But I'm going to go ahead and introduce that, just so we can have a full comparison for our resistor versus capacitor. So our capacitor, its capacitance is determined by what and how it's constructed. The potential difference across the capacitor depends upon how much charge is on the plates and also on how the capacitance of the actual capacitor. And then we also learned that capacitors stored energy. They store energy when there is an electric field between the plates. And I think electric field and put an E there, but I want the C for the capacitor. One way to write this equation is the 1/2 C delta V squared. So we have some similarities in that the capacitor depends upon what it's made of and how it's made. Resistance depends upon what it's made of and how it's made. The capacitor has a potential difference across it if there's charge. The resistor has a potential difference across it if there's charge moving through it. Now, when it comes to energy, capacitors store energy. Resistors do not. Resistors convert electrical energy to other forms. So we talk about the rate that the energy is converted, meaning energy per time. If you recall, that is power. The power, one way it can be written, is the current times the potential difference across the resistor. An amp times a volt is going to be watts. So the power is how fast the energy is converted. If you've ever bought a light bulb, they're rated in terms of watts. Now, most bulbs anymore, we can certainly buy regular bulbs where we could get a 60-watt bulb versus 100-watt bulbs. But we know now, of course, we have a large move to LED bulbs because they're a lot more efficient. And they also require less energy to be equivalently, however you say that. The same brightness is what I'm trying to get at. 60 watts means that 60 joules of electrical energy are turned into heat and light, not heat, thermal energy and light per second. 100 watts is 100 joules per second. So it's just how fast. Now, of course, a 100-watt light bulb is brighter than a 60-watt light bulb. So a larger power is directly related to, in the case of our regular light bulb, a brighter light bulb. All right. So these are the main equations that we're going to be using. We will have our resistance that's dependent upon the construct of the resistor. Delta V is equal to IR. We'll talk about power again. Well, we'll use all these equations again as well. But also keep in mind that it ultimately is the electric field within the circuit that is causing current to flow. So we must have some sort of potential difference applied to the circuit in order for current to flow. Our battery is that source of ideally a constant potential difference. And thus, as long as we have a complete path through the circuit from one end of the battery to the other, then current will flow. We will talk about series and parallel resistors. Technically, our author covers that in the next chapter as well. So I'm going to be making a separate video for that. And here we go. So as far as this chapter is concerned, we're only covering a small segment of it. I will do a concept video going through some concept questions and an example of type of question you could see. And then we'll move on with talking more about resistors.